Good morning or good afternoon, depending on which part of the country you happen to be joining us from. Welcome to today's Arizo Masterclass webinar, Seeing What We've Been Missing, Technology-Driven Insights into Passive Level Crossing Risk. Firstly, I'd like to acknowledge the traditional custodians of the land in which we meet today. For me, I'm in Rockingham in Perth. So that's the Whadjuk and Burrinjub Noongar people. And I would like to pay my respects to the elders past and present. I also extend that respect to all Aboriginal and Torres Strait Islanders peoples with us today. Level crossings remain one of the most complex and persistent safety challenges across our rail network. Whilst enormous progress has been made over the decades through engineering upgrades, education campaigns and enforcement, passive level crossings continue to account for a disproportionate share of serious accidents and fatalities, particularly in the regional and remote areas. From an Arizo perspective, this is exactly the kind of systemic safety challenge that demands national collaboration and evidence-based standards. Arizo's role is to work with industry and governments to develop harmonised standards, codes of practice and guidance that shifts safety outcomes across the networks. Through our standards development program and industry committees, Arizo has supported guidance on level crossing design, risk assessment methodologies, signage and road rail interface management. We have also played a key role in supporting the ongoing evolution of ALCAM, which remains a cornerstone tool for assessing level crossing risk nationally. Now, across Australia, the majority of level crossings are passive, over 20,000 of them. Many are in locations where installing active protection is neither economically or practically feasible in the near term. If we are serious about improving safety outcomes, we must be smarter about how we understand and manage risk at these sites. And that's why today's topic is so important. Technology-driven monitoring and advanced data analytics give us the opportunity to move from a reactive model, where we primarily learn from incidents and near misses, to a proactive, behaviour-informed approach. By observing real-world interactions at passive crossings, we can begin to understand precursors to safe outcomes, patterns of approach speeds, hesitation, sightline limitations, drive distraction, environmental influences, and more. Ultimately, improving safety at passive level crossings will require more than just infrastructure upgrades alone. It will require insight, deep contextual data-driven insight into how people and systems interact at the road rail interface. So today's presentation challenges us to rethink how we see risk and how we act on it. So today I'm delighted to introduce our presenter, Nahershan Nataraj, who will take us through how technology can help us see what we've been missing and how that knowledge can translate into safer outcomes across the network. Nahershan leads the development, translation and commercialisation of advanced technologies for the rail sector at the Monash Institute of Rail Technology as the Deputy Director. His work focuses on bridging cutting-edge research with real-world operational capability and measurable financial outcomes for the industry partners. With a career spanning aerospace and rail, Nahershan brings deep technical expertise alongside a strong strategic and commercial lens. He is particularly passionate about innovation that delivers practical value, integrating engineering insight, digital technologies and industry needs to improve safety, asset performance, reliability and whole-of-life cost efficiencies. Now, before I hand over, I'd like to remind everyone to enter any questions you may have into the team's Q&A at any time during the presentations, and I'll present those to Nahershan at the end of his presentation. I would now like to hand over to Dr. Nahershan Nataraj for his presentation.
Thank you, Chris. That was an excellent summary of the presentation. So thanks for that, and good afternoon, everyone. It is a real pleasure to be meeting all of your digital personas. I too would like to start off by acknowledging the traditional custodians in the lands on which we gather. For me, joining from Clayton campus at Monash University, it's the land of the Kulin Nations, and I pay my respects to their elders past and present. Someone asked me just before, have I joined these sessions by Arizo or previously RISB? When I joined the industry, this was a forum where I learned a lot from, so it's great to be contributing to the conversation here. Chris has already done a remarkable job introducing the topic and the subject matter, so I can jump straight into it. In today's presentation, I want to go through three things. Firstly, I want to go through the background and examine how we currently measure and manage risks at level crossings. And then I want to talk about a technology-based solution that will help us not just understand the behaviors that are driving risk at level crossings, but also measure the effectiveness of different controls in place. And finally, I'll walk through a couple of real-world scenarios where we've applied the technology to draw some insights that will hopefully help us start thinking about this problem in different dimension and come up with a more scalable and more effective solution. So with that, let's start, and I'll just give a quick introduction to the Monash Institute of Railway Technology, where I work. So the institute is over 50 years old. It is one of Australia's longest standing and possibly the largest applied rail research group across the country. We work across a number of deep rail subject matter expertise areas. And one of the core differentiators between IRT at Monash and most other research institutes is we are fully industry funded, which means every problem we work on and every challenge we work on is driven by real operational challenges that the industry actually faces. So we've got a really good understanding and really good relationship with most of the industry. With that said, that same relationship and that same understanding of the problem is what's shaped this work that I'll be talking about today. Some sort of, although we've been here for a long time, our proudest part of IRT is the impact we've been able to have on the industry, and it's a real privilege to be serving the rail industry in that notion. There are some technologies where we've been the world first to pioneer, starting with asymmetric wheel rail profiles, instrumented door cars, and phased array technology. These are just some of the technologies we've helped introduce, and we hope what we're working on today goes on to shape the future of Australian railways. So let's get right into it. Chris already gave a bit of a pretty good introduction to this. Level crossings remain one of the most persistent point of risk across the railway network, where rail and road intersects, two very different operating systems collide. And that interface continues to produce serious consequences. Looking through some of the numbers, we've got over 18,000 according to me, probably 20,000 according to Chris, but different sources give different numbers of passive level crossing nationally. Thousands of near misses every day, hundreds near misses over the years, hundreds of collisions, and dozens of fatalities. So it's a very serious problem that we need a solution for. Of course, there's an obvious solution to this, just grade separation. If only we had all the money. Well, that would be easy. However, in a resource-constrained environment, grade separation is only feasible for a small number of high-density metro environments. So we need a different solution, a solution that is scalable and effective. Scalable not just in terms of its applicability to regional settings, but also financially feasible. And it's got to be able to improve safety outcomes in a measurable manner. Fortunately, we're not working in a vacuum. There's already nationally coordinated effort to address this issue. The National Level Crossing Safety Strategy addresses this through 4 important pillars. And it's important to touch on this because the solution we are putting forward here fits within the same framework. First, there's the education and enforcement, increasing the awareness of what's driving the risk in level crossing for the different users, driving the expectation of what is a safe behavior, reinforcing those safe behaviors. Then we go into asset technology and innovation, where we leverage engineered controls, scalable solutions that reduce the risk in cost-effective ways. Third, data improvement and knowledge management, ensuring we collect, structure, and analyze crossings data in a nationally consistent manner. Last and most importantly, national coordination. To learn off each other, we have to have systems that diffuse the learnings across the whole of system. This framework is quite sound. And I don't have a major critique on this framework. Where I see we have areas to mature is in our ability in that asset technology innovation and the data improvement process. How can we use technology to better understand what are the drivers of risk, some granular information about what is exactly driving the risk, and therefore putting the controls in place that match this. Before we go on to what is possible with technology, let's start at a good the good base that's already been set up through the ALCAM framework. The ALCAM framework, which is the Australian level crossing assessment rule, that assesses the safety risk at different level crossings and ranks them according to a risk score. To understand this is fairly straightforward. The risk, as is generally understood in every other forum, risk is the expected consequence of a catastrophic or an undesirable event. The ALCAM framework takes exactly this, so it's very straightforward to understand. It rates the risk at each level crossing as a likelihood of a particular adverse consequence happening. So how do they measure consequence? It's the expected number of fatalities. So you convert every outcome into a number of fatalities, and that's a consequence. The likelihood is addressed in a slightly more nuanced way. The likelihood is affected, according to the ALCAM framework, by two factors: an infrastructure factor and an exposure factor. In the infrastructure factor, the framework takes into consideration how the setup of the level crossing itself contributes to the risk. It could be things like sighting distance, approach angle. And the exposure factor takes into account the human behavior, although in an indirect way. It takes into account human behavior by accounting for accidents in the region and near misses in the region. Now, it's almost pretty obvious what I'm going to comment on next. That way of measuring likelihood is a lagging indicator of risk. It acknowledges risk after an adverse event has happened or when a near miss has happened. It relies on these things being recorded and informed. Now, if you really want a systemic solution, you cannot have a learning cycle where you put in a solution, wait for accidents to happen or not happen, and then scale those solutions. And when you put it in, how do you know how effective you're spending your money in terms of controlling the risk? Let me make this a bit more practical. Hopefully a situation that's familiar and in which a lot of you are making some sound decisions on. So let's say you have a particular site. You have a particular site, and then you assess the risk at that particular site. Risk, as we already established, is consequence times likelihood, and then you establish the risk for that particular location. Of course, you have an acceptable risk threshold, and this risk is above that, so you're going to have to do something to bring it down. Now, importantly, we use SAFAR principles to assess the controls that we put in place. Now, SAFAR requires balancing of two things: risk reduction with cost of implementation, because that's a very practical way to look at it. Now, I should have probably drawn this graph here, but if you had to draw a graph of risk versus cost, on the x-axis, imagine there's percentage of risk reduced, ranging all the way from no risk is reduced to 100% of the risk is reduced. And on the y-axis, we have cost. You'd know, all of us already know, at least intuitively, 2 points on this curve. One, for 100% speed reduction, you've got to eliminate the risk. So grade separation, prohibitively high to scale across the entire nation. The other point is, well, you don't do anything, therefore there's zero cost of controls, but you're also not controlling the risk anyway. So it's the in-between in which we're making all of our decisions, and that part is fairly opaque at best. How do you know how much risk is being reduced for using the different controls at different sites? And it's that elasticity. How does the cost of a solution affect the risk reduction? That's what we're trying to understand through this and help decision makers make more safety and cost-effective decisions. Now, the crux of it is, the accidents are consequences. Behaviors are what's driving those consequences. And there could be certain conditions driving those behaviors. So what we are looking for is a technology that helps us understand, measure and characterize human behavior, and then also measure all the associated drivers that could affect human behavior. What do I mean by that? So let's go through some of the examples we have here. There could be a level crossing where under normal circumstances, there's a high level of compliance for the rules in place. However, under different weather conditions, you could notice that the compliance starts dropping. It could be because the roads are wet. It could be because the visibility is affected. So what you want to be able to do is get a technology that measures the behavior and the variation in the behavior and segment into different drivers of those behavior. That could be weather, it could be traffic classes. And one of the common hypothesis that's put out there is heavy vehicles are large contributors to risk at level crossings. Now, there are some data points, but is it systematically true at every level crossing? Not sure. Then we also put in different controls, but we don't know the level of compliance if we're only waiting to see if it stops an accident. So we have to start measuring things at a behavior level. Of course, I'm leaning into a technology that helps us measure and characterize and give us more insights to make better informed decisions. However, when we spoke to people in the industry early stages, they wanted this technology to be reliable, which is a no-brainer because you're going to make consequential decisions with it. You wanted it to be low cost because you wanted to be able to scale across multiple sites, and you wanted to be privacy preserving. What we are going for is an exercise to better understand the behavior that's driving risk, not a surveillance exercise. And in our efforts to sort of implement this trial this technology and showcase how it works in different jurisdictions, we found the fact that we're not collecting any personally identifiable data meant that we got community and council support so much faster. Why are we in a position to sort of talk about this technology now, which I think we couldn't have spoken about even 3 years ago? It's because there are 3 key advances in technology that really support this. Firstly, there's advancements in sensors, advancements in applied AI, and distributed infrastructure. When I talk about advancement in sensors, sensors are becoming smaller, more robust, consuming less power, and delivering significantly more capability in terms of insights and measurements. This allows us to deploy this in an unobtrusive manner with minimal footprint and get highly reliable data. Then moving on to applied AI, I'm sure there's not a day when you don't talk about or use AI in your work. But what it really means is it's now given us the ability to get this multimodal data from different types of sensors, complex information, and convert that to insight fairly easily without the requirement of a team of tens and hundreds of programmers, drawing insight out of it. And then distributed infrastructure. Now, edge processing capabilities means we can process so much of the device so much of the measured data at the point of measurement. This means you don't have to be transmitting data from whatever place you collect data to a remote site through this big broadband needs. And you also don't need to wait for the entire data collection program to be done before you can understand how the system is performing. So we built a technology that is capable of doing 3 things. It's able to observe the risk in a particular location. It's able to characterize those risks, and then it's able to intervene. For this particular presentation, I'm only going to focus on the observe and characterize part. Now, when I say observe, the system captures critical behavior and environmental data in an automated and non-invasive manner. It's modular by design, which means the same system can be placed in a variety of regional settings without the need for any hardware modification or any customization of that sort, which really reduces the cost of the system. And importantly, it's a robust measurement system. When you put these systems out in the remote areas, in the regional setting, you don't want to be having a device that you need to go in and checking and fiddle, and there's some reliability issues. And when it comes to characterization, this is where we take the raw sensor data and transform it into structured behavioral insights. We use AIs and a bunch of data science techniques to get there. And all of this is happening on the edge. It's happening remotely. And the insight that's gathered is then communicated out through some web application or a dashboard or however you want to visualize it and make decisions from. So let me actually show the device that's been built. We built 3 generations of this device. We call them Mark 1, Mark 2, Mark 3. And the focus each time has been to make the device simpler, and the operations of the device to require less man hours and less tools, and easy to deploy in different regions. So let me talk through the device from those 2 perspectives: the architecture and the operational, how you sort of implement this system. From an architecture perspective, this system is simple by design. At the top, you've got the solar panel. That then powers the system locally. What does this mean? It means you do not need any power line to be supplied to this system. That is important in a regional setting. If you want to get comms and power, you limit where you can implement this technology or the cost of implementing this. Below the solar panel, you've got the antenna that can then helps us connect to the device and the device to connect to us, which means we're getting these insights as it's measuring and characterizing risk in close to near real time. Then you've got the LiDAR, which is the core sensing technology. We've chosen the LiDAR for a number of different factors. It's to do with what it can measure. LiDAR gives you a point cloud representation of the environment that it sees. And I'll talk about some of the insights that we can get out of it. And more importantly, what it can't measure. LiDAR does not measure any personally identifiable information. For example, it doesn't register number plates or anything, but it can definitely tell you what class of vehicle it is, how fast it is going, what's its trajectory. And then all of this connects to the equipment cabinet down here, and that's where we have the power solution, the smarts for processing, all of which is happening locally, and the coordination of the information to be sent out from there. Let me talk you through, showcase an actual example so we can visualize the sort of insights that are coming from the system. On the left here, you have a typical, it's a Victorian site. It's a level crossing that's not used, but the controls in place are similar to other level crossings anyway. So we put it here to test the system. You see the vehicles going through there in the video footage, and you see the same vehicle going through in the LiDAR footage that's on the right. You can see the LiDAR footage puts a bounding box or a box around each of the vehicle, and each of the box has a color. So the system is trained with AI algorithms that can detect vehicles passing through it. It tells you what class of vehicle it is. The color of the bounding box, which when the video was showing, was defining the class. It measures the speed at which the vehicle is crossing, not just as the average speed at every single instant, what speed is it crossing at. And then it can also track the trajectory that the vehicle is taking as it goes through the crossing. Now, importantly, it also demonstrates that the LiDAR can capture all of this information that is necessary to make a decision on safety and behavior without capturing any personally identifiable data. More importantly, unlike camera systems, the LiDARs work under any weather condition. It does not need lights. It works under rain. It works under, so it's well suited for the sort of application we need. And let me talk about the behaviors that we're interested in, or that we're trying to characterize. So let's take collision risk. Collision risk depends on how close you are to an infrastructure or another vehicle or even the rail corridor, and how fast you are going. So the two dimensions of measurement, we've already spoken that the system can get positional information and also speed information. And if you map those on a plot for a particular site, you'll be able to segment. There are some cases where the collision risk is high, either because people are going fast or they're following traffic close. Now, you can then segment that section of the population from the different section of the population where they're following the rules better or exhibiting more safe behavior, and really try and find the attributes under which that more risky behavior is driven. Sometimes it could be blatant disregard for controls, but sometimes it could be systemic. Sometimes it could be to do with lighting condition, class of the vehicle, so some of the factors that I spoke of earlier. The other sort of type of insight that we can gather from this tool is to do with assessing the effectiveness of the controls in place. Effectively, let's take a level crossing here. This is the x-axis, the time axis, and then let's say there's a rail crossing event, and then there's a stop sign on either side of the level crossing. Now, what you want to observe is that the vehicles are coming to a stop ahead of the stop sign or at the stop sign, and you can track this over a period of time to see, is there a systemic pattern to the compliance to this control in place? Now, let's move to the application of the technology. So how have we applied this technology in the field, and what insights have we gathered? So this is a Victorian site. All the site identifiable information has been removed, but the necessary context has been kept. So you've got a level crossing and an intersection, and there's an asymmetric control that's been imposed in this place. You've got a stop sign on one side and a give way on the other side. So, and it's not atypical to find such an asymmetric control across a level crossing. And this also shows where we placed our measurement system in relation to it. Now, one of the advantages of the measurement system, LiDARs have quite a long range, which means the system can be recessed quite far from the road and still get all these important insights. A question we get often is, would the act of putting a measurement system in itself influence human behavior? We do surveys before we put the system out there. So we have an understanding of the typical behavior before we put it in, especially for these trials. And we've not noticed any change in behavior except when we are physically there setting up the system. Some people may stop, slow down just to see what's going on. But after that, people forget the spatial awareness is not as high as we would hope for safety reasons. Now, what are some important characteristics of this level crossing aside from the asymmetric control? It's that the traffic through the level crossing will not just be affected by the controls here, it'll also be affected by the traffic flow further downstream. Because if there's a congestion here, it starts backing on to the level crossing itself. So we have to see how that influences this region. Now, I'll go through the system setup. The important part is I've already described the setup of the system, but operationally, what does that do? It means we find a local supplier or a contractor who would rent out this concrete block with the winch that they come stand in. They come deliver it on site, then we go. It takes about a couple of hours to put on the solar panel, the antenna, the LiDAR, and then bring them up to the equipment cabinet. And then you've got access to real-time data that you can log in, check how the measurements are going. So this happens in a matter of like 2 to 3 hours. We've set the whole thing up. It takes less time to set it up than to get to the site. Now, let's walk through the insights for this particular site. Let's start with the basic traffic composition. Over the 2-week period, we noticed that the average weekly traffic across this site is about 3,500 vehicles. The distribution is more or less consistent across both weeks, and we find 85% of the traffic in this crossing for the period we measured was light vehicles. Again, our definition of light vehicles are vehicles that conform within a certain size spectrum. Heavy vehicles represent a much smaller proportion, roughly 15% in this particular case. Motorcyclists and pedestrians, you can't even see them because they're so small in this scale. So that gives you a characterization of who's using this level crossing. Now, this is important for two key reasons. One, it shows behavioral differences. It shows a different class of groups and how they're represented. So we can study the behavior of light vehicles separately to the heavy vehicles. It also gives you an important insight into exposure. There are 7 times or 8 times as many light vehicles passing through this region as a heavy vehicle. Of course, the consequence of a heavy vehicle collision might be greater, but the probability-wise, the light vehicles represent an overwhelming proportion of the traffic. So now when you think of risk, it starts, you can break it down and say, where exactly is the risk compromise happening from? And any marginal improvement in behavior improvement for light vehicles will have a significant outcome because it represents a greater proportion of the traffic flow here. Now, the next thing is we can get into a more granular understanding of how the traffic flow changed through the week. Now, important to note that the y-axis here is on a log scale, so any small dip here could be a larger dip in practice, but I had to use a log scale because pedestrians and motor vehicles were so small in numbers. What you'll observe is that there is a clear distinction between weekday and weekend traffic. Now, would you have this intuition before we did this study? Of course, we know the weekend traffic is going to be different between weekday and weekends. But now we have a quantitative metric. We know how much of the risk is happening on the weekend. Well, how much of the traffic is flowing through on the weekend versus how much is it flowing through on the weekdays. We're still not come to behaviors yet. We're still talking on the level of utilization. Heavy vehicle activity remains relatively consistent during weekdays and then drops noticeably over the weekends. And now the pattern is something that aligns with the site's regional freight profile, suggesting this route probably serves some level of structured commercial activity during the week. Light vehicles also have a bit of a dip during the weekend, and really motorcyclists or pedestrian, there are no motorcycles here, but pedestrian use is minimal, although there is still some level of pedestrian cycles. Now, what this helps you, if you know where the risk is coming from, what point of the day, what days in the week, you can start thinking about different controls that are not sign-based. Could you coordinate traffic better? Could you speak to the commercial people who are using the route to say, can we decouple your peak period with the passenger peak period? So it really opens you up to coming up with some creative solutions for risk reduction. Now, let me get into the next thing. Now, this I hope people find interesting. What you have here is a measurement of compliance to different controls in place. What are the two controls in place? There was a give way sign and a stop sign. Now, one graph here shows the compliance for light vehicles and the other one shows the compliance for heavy vehicles. The blue, dark blue, shows what fraction of the vehicles passing through on Tuesday complied to the stop sign, and the light blue shows what fraction of the vehicles passing through on Tuesday complied to the give way sign. Now you're starting to understand the behavior at a much more nuanced level. The heavy vehicles in general showed higher compliance to the controls in place for both stop signs and give way compared to the light vehicles using this site. Second, the stop sign, compliance to stop signs was greater than compliance to give way signs. Both of these insights are fairly intuitive. Well, at least the second one is fairly intuitive. That stop signs when you look at a stop sign, you think it's an instruction. You say stop, whereas a give way is subject to interpretation, so therefore people may not follow it. You may have a question as to, so what rule basis did we set for the give way sign? We said under the best case scenario, so where conditions are dry, your car's braking system achieves, sort of the third quartile performance for braking, you have, what is the minimum speed people need to cross over to make sure if they put the brakes, they won't come to stop at the level, at the railway tracks themselves. So looking at these two, we now have in this site, the myth that heavy vehicles don't, are exhibiting more risky behavior is not true. In fact, they're complying better than light vehicles. Putting this with the earlier insight we had that light vehicles represent more of the traffic and their compliance is lower, I would say in this particular location, there's room to sort of start thinking, if you wanted to put compliance up, it should be, how do you move the light vehicle compliance up? And you can already see, if you put a control in place, you can get another measure of the performance, and you can do an A/B comparison and say, did the control make a statistically meaningful difference in risk reduction? We can also go one step deeper. For the vehicles that didn't conform to the controls in place, what was the nature of the non-compliance? Was there blatant disregard for the controls in place? For example, if there was a stop sign, did they at least try to slow down or stop? Did they try to slow down, or did they just speed right through? What we found again is that in a heavy vehicle case, there was at least intent to comply in half the cases for both the give way and the stop sign, because they at least slowed down to some level to try and comply to the controls. Whereas the light vehicles, almost 80% of the cases where there was non-compliance, it was a blatant disregard for the rules in place. Now, in that case, for light vehicles, again, I'm not forming conclusions, but what that suggests is it's an enforcement thing, because there's blatant disregard for the rule. Now, there was also another type of risk to be assessed in this location: stacking. Stacking is when a vehicle when a vehicle or part of the vehicle comes in and stops in the rail corridor. Because of the complex design of this particular level crossing and the flow being limited by the flow through the intersection further ahead, stacking was a real risk at this site. And we could measure it because we could track the trajectories of each and every vehicle that's passing through this region. What we found was that there was a strong correlation between traffic density and the probability of us observing a stacking event. In fact, we found every time the stacking, the traffic density went about 30 to 40 vehicles going through the section in an hour, inevitably we saw at least one stacking event. Now think about that. What does this insight mean if you're someone who's deciding on controls? It's not about a flashy red light, or it's not about bells and alarms for the controls. It's about when a driver who's intending to follow the rules is crossing the stop sign, how do they know if they can cross over the entire railway line or not? So it's about, how do you give them awareness of the traffic flow downstream so they can make an effective decision? Already you can see how this insight can change the sort of safety decisions we can make. Summarizing this site, stacking presents a key risk. Compliance to and stacking is strongly correlated to local traffic density. Compliance to the controls in place is relatively high. I say relatively high because it's above 80%, but I need to see it across multiple sites to say if it's statistically, if that high actually means it's high or low. Implications, well, if you're going to make a decision here, you've got to think about, how do I stop stacking? And if you're going to increase your compliance rates marginally, there's not a lot of room left from 85% to like 100. So what is going to be the cost curve associated with that? Now, hopefully this has demonstrated the quantitative understanding of behaviors can really help you make better decisions about risk control. I'll also quickly touch on a different upgrades we did to the system, and a different site in which we tried, and what sort of insights, different insights that trial has given us. The upgrade we did to the system was to, instead of putting it on a concrete block, we put it on an equipment tray, an instrument box. This gave us more control. We didn't have to find a contractor to move a block. All of this could be done with manually managed tools themselves. So it meant we've gotten even faster, even more nimble at deploying this, or the solution is even more nimble and can be applied in more regional settings. Now I'll talk about the regional setting in which this Mark III of the technology was trialed. It again, it's a standard level crossing. In this case, symmetric control, stop signs on both sides, but this stop sign also had some warning capability. So it had different writing that could appear depending on the condition. And we placed 2 sensing units. Now these sensing units are modular, so again, showing that they can fit complex road and rail intersection profiles. Now, I'll go through this faster because we've already been through this exercise once. The first observation we had is this site has 1/10 the traffic flow of the Victorian site. So the weekly traffic is in the order of 300 at best. Secondly, there is a lot more variability in the traffic that's flowing through this region, typically a peak on Monday. Now, later, we also found out that there was an event of some industrial event happening in a nearby region, which may have affected traffic flow. Now, our learnings from that is when a region has low traffic flow, you might have to take a longer sampling window, longer than 2 weeks, to make sure that your data, what you're observing, is a good statistical representation of what's happening in that region. I've presented the compliance graphs that I showed previously in a different way to impress upon you a different point. When you take the light vehicle compliance distribution, you actually see 2 peaks, 1 peak or 2 groups of behavior, 1 group of behavior here and another group of behavior here. The second group, there's high level of compliance and low variability in that high level of compliance. Whereas this group, there's lower level of compliance, but also more variability in that low level of compliance for light vehicles. So now you can check the different attributes we have: time, traffic density, lighting conditions, and see, is there some attribute that best separates these 2 groups? And then you know what that is, the lines along which the control needs to be implemented. Similarly, if you take the heavy vehicle compliance, well, the heavy vehicle had just 1 group of behavior. Effectively, it's slightly lower than lower level of compliance in the light vehicles, and it's slightly more spread, but they're not 2 different groups of behavior. Again, important insights that we would not have known. And also it shows how different this particular location is from the other location we looked at, that it again reinforces that not all level crossings are created equally. Now let's get into the same graph I showed before, which is for the cases where there was non-compliance, how many of those cases, or what proportion of those cases, was blatant disregard for the rule? In this particular site, most of the cases, both for light vehicles and heavy vehicles, were blatant disregard for the rule. Now, again, this would make you think of a solution that's different to the previous site. And then also you can see, if you put a control in place, how it influences these behaviors, compliance, and then also know what drivers are driving those behavior changes. With that, I've gone through both of the use cases that I wanted to share today. Now, a fun part about doing these presentations is to talk about what the future could be. The future is driven by the same technology capabilities that we're talking about now: advanced sensors, applied AI, distributed computing. And this research is quite advanced in that I think I would expect to see this in the next 5 to 10 years, if not here at some part of the world, where you have automated units in your vehicles and the infrastructure is controlled by some control unit sitting as part of the infrastructure. So let's say a car's coming in this case into a roundabout, it sends out a request to the control unit. The control unit coordinates it and provides it a token for it to pass through safely, not just safely, but also optimize throughput. I think the same technology will come into level crossing control. And where is the technology I spoke about, where is that heading? Well, we've already got the ability to sense and characterize risks. Now, the next step is, can you communicate this insight in a near real-time fashion to both road users and rail users so that they can make better decisions? And not only can you communicate this increased spatial awareness, can you actually prompt what behavior they should be doing? And that's the next steps of the research. So with that, I come to an end, and I want to thank Arizo for this opportunity to contribute to this very important conversation. And it's been a privilege to share this with all of you, and I'm keen to hear your perspectives, any questions you may have.
Wonderful. Thank you very much, Harshan. I really found that interesting. Having been involved in risk assessments for many, many years, I understand that likelihood is very much a subjective assessment. So tools like this and that data that you collate will take it away from being that entirely subjective idea to actually got some real guts that you can actually use. So really, really interesting. Great presentation. Thank you so much. We do have a few questions. So there's a few questions around this one. So I'll just sort of group these together. So the mobile data collection system seems to be assessing driver behaviour at a level crossing in isolation of driver behavioural changes when a train either is or isn't in the vicinity of the level crossing, and the level of conspicuity for the level crossing stock that the driver is seeing. Is there any plans to refine this analysis in the future?
So, well, great question. I'm hoping my slides are still on there.
Yes, they are.
Yeah, okay, perfect. So I'll go through an example which I sort of brushed through. So I haven't showed in the specific examples because it is too granular to get into, but effectively, when the rail crossing events happen, but from two reasons. One, we anticipate it happen because when we install it, we know from the operators when the rail is going to pass through the region. And secondly, the LiDAR can also look at the train. So we have a demarcation to say, this is when the train crossed this crossing. And we do notice that the behavior, even in this like mock example I have here, I've tried to show that the behavior around the rail crossing, which I've drawn by this gray line, is different to when the rail is not crossing. So the train passing definitely has a view. In fact, one of the things I think drives risky behavior is when people don't see a train, they feel like they can take a risk. And in fact, the greater the sighting distance they have, the less they are going to slow down if they don't see a train. So it's very interesting. So yes, the technology can already do that, and I think you can have a whole nother session about how increasing visibility and the passing of the train affects this entire behavior.
No, that's really interesting, and I think there would be a lot of interest in that side of things. Another question here I've got is I'm keen to hear a little bit more about how the system defines compliance with a give way sign, as it's based largely on driver perception of oncoming traffic when there's no requirement to stop. It seems hard to assure compliance in such a scenario. So you can just talk a little bit more about that, how you define compliance in that give way scenario?
So, well, that was one of the challenges we had at the start. So the way we did it was, you don't have to stop. The give way doesn't imply you have to stop, but you should slow down to such an extent that should you need to stop, you can stop.
Right. Yep.
And so we said, if a typical car has a certain deceleration profile within some sort of band, and you say, given that deceleration profile and the roads are dry, so under the best possible scenario, you can achieve that deceleration profile. How much distance would you need to stop, should you need to stop? And we just said, did you slow down enough such that if you applied the brake at the absolute last minute, you won't come to a stop within the danger zone across the track? So that was the measure of compliance to give way.
I understand. So it's in a similar way to braking curves work on ATP, rail systems, ETCS, that sort of stuff.
Yes.
Yeah. Oh, fantastic. Another question here, is the data, the level crossing data that's been collected, is that published somewhere, or are you preparing to publish a paper on this?
So this work was funded through a federal grant, and we put together a report for them. I don't know if they're going to make the report public, but we've not published anything except provide reports to the federal agency.
Yeah, oh, hopefully it is, because I'm sure there'll be a lot of interest in this. Another question we've got here is the near miss data in the National Rail Safety Data set is affected by a lack of consistency about what's defined as a near miss and what gets reported by rail traffic crew. Could the technology you presented be used to improve that data by creating and applying a standard definition of what is a near miss and then feeding that information directly into ONSA as a notification?
Absolutely. And I think those, you know, even when I said compliance to give way, it raised a question of what exactly is compliance to give way. And it's going to do the same thing with near misses. It's like, what exactly is a near miss? And because you've got the data, you've got the ability to say, well, can we test a few scenarios that we actually observe, and the system can easily report that downstream. So yeah.
Oh, fantastic. Okay, I've got another question that's come through. How do you see technology-driven behavioural monitoring like this integrating with existing tools like ALCAM?
To be honest, I think that is probably an equally important piece of work that needs to be undertaken collectively as an industry, because as the framework, as with a lot of like the RISB standard, it's about meeting a certain performance. It's not about dictating certain things. The outcome frameworks is good because it has every element of risk, likelihood, consequence. But now we're saying, how do we feed in this data as an input to the likelihood? And we have to. I'm sure there's going to be working across different jurisdictions, different people who work with ALCAM, but that I see as an important step, but something that's very achievable, because we're moving from a subjective to more data-driven, and it's about how do you consistently measure and structure this data in a way that it can feed and scale across different sites.
Yeah, no, I think there's a real opportunity there. So that would be really interesting if we can go down that road for sure. Yeah. From a cost-benefit perspective, how scalable are these monitoring solutions across regional and remote networks? And what would be the practical barriers, whether they be technical, financial, or regulatory, to some broader deployment?
I think what would I say? I would say the will of the industry would be the barrier, because if you think about it, we're not saying you need a device for every location, right? And so you don't need to build hundreds or thousands of this. It's about having a structured program to say, well, I'm going to work through my highest risk to lowest risk. I'm going to try and characterize the risk. Once you get the system, you put it down, it monitors. It takes maybe 2 people to set it up, maybe 10 hours of manual labor just to set up and configure things. But after that, it's just reporting that. And until you choose to move it, you keep getting data about a particular site. So the cost, I think, is as low as it can get. It could probably get lower if you manufacture this in volume, but I don't think that's again where you want to go down. And this right now, it's more it's an important insight gathering tool. So you don't need to build one for every single site. So I don't think finance are going to be the thing. It's about genuine interest to understand and manage risk with these insights, rather than just saying, I'll wait for an incident to happen. So,
yeah. No, that's great. Another question here. So great presentation, thanks. My question is about applied AI. What specific tasks does AI perform, e.g. Detection, tracking, prediction, anomaly detection? Also, are models trained per site, or they're just generalized for crossings?
So the key task the AI is doing is detection. There's nothing predictive in this particular scenario. So that task once it's trained, it can go to every single site. So it's not being trained once. It's trained once and then launch at every different site. The rest of it is a real measurement, how it's moving, how close it's getting to infrastructure. All of those are measured things. So that's not AI driven, and therefore doesn't need to be tuned per site.
All right, not a problem. Well, look, thank you very much. I think that's pretty much all we have time for. So I'd like to once again thank Dr. Nataraj for his presentation today. Really, really interesting. Thank you very much to everyone who attended today. I would like to hopefully welcome you all back for our next masterclass. So please keep an eye on the emails and the Arizo website for our next masterclass. But until then, have a safe day and look forward to seeing you all again in the near future. Thank you very much.